Many people have seen the blue glow of a nuclear reactor, either in life or in a picture. This blue glow arises when a charged particle, such as an electron, passes through a specific medium, water, at an enormous speed. This specific blue radiation is called Cherenkov radiation. We will not go into how neutrons are being generated, but only in how we can use them for diagnostic purposes, such as materials analysis. Neutrons can also be used to image certain objects, such as shown here with the ancient Van Leeuwenhoek microscope, but this will be out of the scope of this MOOC. Neutron and X-ray diffraction are quite similar, but due to their different scattering properties by the atoms, they interact differently with matter. But they have wavelengths in the same window. X-rays primarily interact with electrons of the atom, making the diffracted X-ray intensity larger for atoms with higher atomic number. On the other hand, neutrons interact with the nucleus of an atom, and so the contribution to the diffracted intensity depends on each isotope. Light elements are good to see with neutrons in contrast to X-rays, and so lithium and hydrogen are nicely be analyzed in specific matter with neutrons. As said, neutrons can distinguish between different isotopes of the same element, such as hydrogen and deuterium having the same element assigned by a capital D. So, for instance, we can play with the contrast by replacing water H2O by deuterium D2O. Interestingly, vanadium scatters X-rays strongly, but its nuclei hardly scatters neutrons. This is why it is often used as a container material for neutron analysis. Apart from the difference in scattering properties, neutrons have a much lower energy compared to X-rays, millielectron volts versus kiloelectron volts. Hence, there is hardly any risk of thermal damage of sensitive samples. Similar to X-ray diffraction, observation of neutron diffraction signals require also long-range order, and so constructive interference occurs according to Bragg's law, and thus we will typically record it as a function of 2 theta, where the peak position gives information on the lattice spacing. In order to relate XRD and neutron diffraction, it is best to draw spectra as a function of d, the interplane distance or spacing, as defined by Bragg's law. Hence, that rules out the instrument parameter of the wavelength lambda. Here we will show you various lattice spacings via the HKL values of silicon, an interesting electrode material for lithium-ion batteries, for copper K alpha and a neutron wavelength of 1.5 angstrom. Following the strong 111 peak, we see that the recorded XRD and neutron diffraction spectrum would have been the same if we would have plotted the spectra versus D by recalculating the spectrum based on the applied wavelengths. Since neutrons could easily pass heavy atoms, neutron diffraction is well suited for analyzing complete cells with metallic casings, as we will see next. Since it is possible to monitor light elements with neutron diffraction, we modified spindle type lithium manganese oxide, a positive electrode material for lithium-ion batteries, with a strong acid till various pH. The material partly dissolves under extraction of lithium, manganese and oxygen. At certain pH, not only lithium is being removed, but also hydrogen ions, protons, are inserted. The structure itself remains intact. Only lithium ions are gone and partly exchanged with protons. This cannot be seen with X-ray diffraction, but it does with neutron power diffraction. Many more peaks are observed, arising from the planes where lithium ions are. At a treatment with a very strong acid till very low pH, additional peaks arise, indicated by the yellow circles. These peaks are solely due to the protons that were inserted. By analyzing the peak position and intensities with models such as Rietveld refinement, the composition and ion position can be calculated. The results of the compositions are given in the plot and were already shown in the XRD results. As said, modeling also gives fine structure of the crystal. For this material, it turns out that protons does not go to the position where the lithium ions have been removed. In crystallography, the position is called the 8A position, and it's a tetrahedral created by 4 oxygen ions. The lithium ion then is exactly in the center of the tetrahedron. In contrast, the protons prefer to go into the corners of the tetrahedron. These positions are known as the 96G sites. By the way, the numbers 8 and 96 before the A and G indicate the number of equivalent positions in the unit cell of the crystal. These new positions have implications on the various planes in the crystal and are nicely visible with neutron powder diffraction. Structure analysis can also be done operando in a full cell. This is possible due to the deep penetration depth of the neutrons and the possibility to analyze structure changes. This has been done here in the Center for Science and Technology of Advanced Materials at the National Nuclear Energy Agency in Indonesia. They record neutron diffractograms of the full cell. It is stressed that the diffractogram is a combination of all materials in the cell, meaning the casing of iron, the current collectors aluminum and copper, and the electrode materials graphite and lithium iron phosphate. Monitoring the state of charge, SOC, at various percentages, it is possible to follow the changes in the structure. It allows also to identify degradation products and therefore the state of health of the battery. In summary, neutrons have deep penetration. Neutrons allow the study of bulk and internal structure of materials, such as in operando batteries. Neutrons are highly sensitive to light elements, like X-rays, and can be measured way better hydrogen and lithium positions. It allows isotope differentiation. Neutrons can distinguish between different isotopes of the same element, such as hydrogen and deuterium. For instance, allowing to play with the contrast by replacing water with DTO. It is particularly interesting to combine the neutron powder diffraction results with X-ray diffraction data for structure analysis.